Welcome to this edition of Lakeside Physics. In this video, we will give an introduction to circular orbits. So when we talk about circular orbits, we're talking about, for example, the moon orbiting around the Earth or the Earth orbiting around the sun. It is the force of gravity that acts in this case as the centripetal force for the orbiting objects. Now, you might ask yourself, why is it that the moon doesn't go crashing into the Earth if there's this force of gravity pulling the moon towards the Earth? Well, it's the same idea as when we think about a ball being swung in a circle and that there's tension inward. Why doesn't the ball end up flying towards the center of the circle? It's because the object is in motion initially, and so that force is causing it to change directions off of its original path. So if the moon wasn't moving, it would go crashing into the Earth. For circular orbits, the orbiting object must have a constant speed. This requires two things. One, that the velocity vector is perpendicular to the acceleration vector, and two, that there are no other forces present. For real orbits, these two assumptions are generally not true. The reasons are, most objects have elliptical orbits where velocity is not perpendicular to acceleration, and other forces are generally present. Other forces due to planets, dust, atmospheres, etc., causing the orbits to decay. We will only be considering circular orbits. So let's do an example. Here's a simple orbit. Imagine that the Space Shuttle Atlantis is in a circular orbit at 150 kilometers above the surface of the Earth. The mass of the Earth is given and the radius is given. Pause this video and try to see if you can figure out what speed Atlantis must be traveling at to be in this orbit. All right. So here's the solution. First, we need to think about the free body diagram. Of course, it's just the force of gravity in this case. And so if we think about writing a net force equation, our net force is equal to Fg, and this is equal to mv squared over r. But we also have a new equation for Fg, big G m1 m2 over r squared. Now notice that the mass of the orbiting object cancels. So because of this is the mass of the rocket is what is in mv squared over r. It is the one that cancels, and we're left with v squared over r equals big G times the mass of the Earth divided by the radius of the circular orbit. Notice that this radius of the circular orbit is also the same thing as the distance between the centers of our two objects. We can simplify this and then plug in our values, and we end up getting that the speed is 7,800 meters per second. Let's consider another question. Now let's imagine that the satellite orbits the Earth at twice the distance of Atlantis. Would the satellite's speed be more, less, or the same as the shuttle? Consider the equation we generated for part B. V squared equals G times mass of the Earth divided by r, so as r increases, the speed will decrease. Notice again that this is completely independent of the size of our object, the mass of the orbiting object. All right, now let's imagine that there is an astronaut in Atlantis. What is the force of gravity acting on the astronaut? We have Fg equals big G m1 m2 over r squared, and we can plug in our values for when it is 150 kilometers above the surface of the Earth, and we'll get 610 newtons. For reference, on Earth, this astronaut would have have a weight of 640 newtons. That's not really all that much different from if it was at the surface of the Earth. Again, that's because 150 kilometers is a small fraction of that total distance to the center of the Earth. All right, so now what would happen if an astronaut were to stand on a spring scale in the Atlantis as the shuttle orbits the Earth? What would the scale read? Well, if you recall, a spring scale measures normal force. According to our free body diagram, there is no normal force. So the scale must read 0 newtons. Why is this? I want to dig into this a little bit further. So let's take a look at this picture. This is from Paul Hewitt's Conceptual Physics, and it shows a person in an elevator. Look, during 4 different situations. The one at the furthest right is when it is in free fall. The elevator cable has been cut, and the elevator and the person begin to fall. And in free fall, that normal force is 0. Another way to say this is that its apparent weight is 0, or the person may feel weightless. In free fall, all objects inside the elevator and the elevator fall together, so there is no reason that the scale would actually push up on the person because they are falling together. This is similar to astronauts that are orbiting the Earth in a shuttle. They are in a constant state of free fall. The only thing that's acting on them is the force of gravity. Note that it's not 0. While they look as though they're floating inside of the shuttle, and they are floating, this is similar to a person who could be floating inside an elevator that was in free fall. They still have weight, but they do not have a normal force, and thus they feel weightless. So let's take a thought experiment, famous Newton's thought experiment called the cannonball. So what we do is we imagine that we're at the top of a tall mountain on which stands a cannon that can shoot a cannonball at various speeds. The mountain is so tall that air resistance is not a factor. You fire the cannon and the ball falls to the earth. You fire the cannon a little faster, it travels a little further. You fire it even faster, it travels even farther, until finally you get at a speed high enough that the cannonball just continues to travel around the Earth, constantly falling towards the Earth, but resulting in it just going into an orbit. Here's another way to think about this. Imagine a ball is fired horizontally at 8 kilometers per second at sea level. In 1 second, the ball travels 8 kilometers horizontally and falls 4.9 meters vertically towards the center of the Earth. The result is that it is the same distance from the Earth's center. In this case, it would be in orbit. And you essentially catch this when the distance that the ball falls in each second is matched by the distance the Earth curves away from the ball each second. The ball will never strike the ground, and it's continuously falling towards the center of the Earth. We say that this ball is in a constant state of free fall. When an object is in free fall, there is no normal force acting upon it. In conclusion, we can think about an object in orbital motion because of the force of gravity as being in a constant state of free fall. I want to end this video by talking about a super cool topic, artificial gravity. Below are images from 2001, A Space Odyssey. In it, there is a space station that rotates, and you can see there's this circular sort of ring piece. That whole ring rotates, and the person in the second image is standing on the inside of this ring, but on the outer edge. This results in the person feeling as though they have gravity acting on them. Now, let's consider weightlessness. We've talked about this in this video already, that weightlessness is when you have no normal force. So if you're in the middle of space, you will feel weightless because you have no normal force acting on you. To generate a force of gravity, you need another large mass. But if you're in the middle of space, you can simulate the effects of a force of gravity by creating a normal force. So if you think back to the elevator example that we talked about earlier, what you feel is based on your normal force. So if an astronaut can continuously experience a normal force, they would constantly feel and experience the effects of having weight while living on a planet without actually being in a place where there is gravity. Alright, so let's do an example problem. Imagine a circular space station where an astronaut stands inside the space station but on the outer wall. Imagine the astronaut and the station rotate at a constant rate. what are the forces acting on the astronaut? In this case, there is only the normal force. How would the astronaut interpret this normal force? Well, they would feel as if they had weight. Imagine a space station has a radius of 25 meters. On the outer wall of the station, an astronaut feels 1.5 times as heavy as they do on Earth. What is the period of the station's rotation? Well, our net force is equal to the normal force, which is mv squared over r. Now, the normal force is going to be equal to what they feel is 1.5 times their weight on Earth, which is mg. Now, if we cancel out the mass, we end up and multiply by the radius, we get that the speed squared is equal to 1.5 times g times the radius of the space station. Now, if we solve this, we get that the speed is 19 meters per second. Now, this hasn't answered our question of what the period is, so we need to now solve for the period. The period is going to be the distance over the speed, or in this case, 2 pi times the radius divided by the speed. So we end up solving this and get 8.3 seconds. That's it for this video. Please let us know if you have any questions, and I encourage you to look up more about artificial gravity. Thanks!